heard many of Doug's other students talk about, massive stars love company. And so I continued that work to look at the properties of massive stars, not just in the Milky Way, but in some of our nearby neighbors like the Large Magellanic Cloud. And so the three sort of motivating questions for the research that I've been doing are basically, are binary properties universal? So if we see that Milky Way massive stars are thought to be close to 100% multiplicity fraction, is this true in other environments? And so what does that tell us about star formation and stellar evolution? And kind of what is the most massive star, right? Is there a limit to how big a star can get? So I usually start with this, right? Because as most of you are familiar with, this is the HR diagram where we have brightness on that side, temperature on that side, and most of the stars live their life along the main sequence, right? And our sun is there. And so most of the guys that I'm interested are sitting up there. So they're very hot in temperature and they're very bright. Typically, they're 16 solar masses or above, most of the stars that I'm interested in, with temperatures greater than 30,000 degrees Kelvin. And just to kind of give you an idea, our sun is around roughly 6,000 degrees Kelvin. So these are guys that are very hot, very massive, and very bright. And but in particular, I'm looking at the very massive guys for a lot of the work that I've done recently. And these are guys with masses that are greater than 100 solar masses. And so typically, a lot of stellar evolutionary codes, stellar population synthesis codes, don't go above 100 solar masses. And so I hope after this talk, you'll agree that they do need to start taking into account these guys. Because there's a lot more than we previously thought. So these guys are the hottest, they're the brightest, and they're the most massive stars we know. And one of the main motivations for the work that I've been doing recently is that when we're looking at very distant galaxies, the ionizing radiation that we see, especially in starburst galaxies, is dominated by massive stars. And so we need to be able to understand the intrinsic properties of massive stars to interpret what we're observing in high redshift galaxies, especially when James Webb comes online. In addition, basically massive stars are where a lot of the heavier elements in the universe are formed through their evolution and through supernova events. That's where we can build stuff that's heavier than iron. And they lead to some really cool exotic things like neutron stars and black holes, and especially the merger of those two guys, right? And so in particular, binary stars were the progenitors to what eventually become black holes. So what we're talking about are the guys that will form these gravitational wave events that we've observed. So most of star formation theory for massive stars kind of falls into primarily two categories. One is what's called monolithic collapse, where once you have your cloud of gas that's collapsing due to gravity, that material is what's going to feed your star, and that's what's going to go into your star until your star turns on hydrogen fusion and radiates whatever else around it away. And what you can see from this model is that most of these star formation events, these seedlings, are happening in the densest regions of this cloud. The other theory for star formation is called competitive accretion. And that idea is that you start with these small seedlings that will be your star eventually, and basically the biggest of those seedlings are the ones who are going to attract more material and so build up your star even further. So you can think of it as basically the rich get richer, right? So if they start off a bit bigger, they're going to be the ones that get more of that mass. And so you can think that basically just from that idea is that, and from the simulation, is that where you want to look for massive stars, you're going to want to look for very dense region where a lot of mass is there for your star to build up on, right? And one of the things that we know from the initial mass function, sorry for the 10-10 diagram, but this is just the easiest one for representation, right? Is that once you have your cloud of gas forming stars, your stars are all of different sizes. And so you're going to get a lot more of the lower mass stars, right? I'm sure Todd has talked about this a lot, right? These guys, there's plentiful. There's a lot more of them. There are a lot more of them by mass. And there's a lot fewer of these massive stars. And they tend to follow a sort of saltpeter IMF in the more massive star range. And so the question then is how many and what is the most massive star that goes into that bin, right? In your cluster that you're forming from your cloud. So I'm primarily an observer. And so most of my work has been done using Gemini, both in Chile and Hawaii, Hubble, both spectroscopy and interferometry, which I'll talk to you a little bit about, and the VLT also in Chile when I had time through when I was in Europe. And so I've gotten asked many questions of where I am now, Florida Tech. So this is a view from space of Florida, and FIT is there. It's on the Atlantic coast of Central Florida. NASA is there, so if you guys come visit, we see space launches, rocket launches once a month, at least. So, and yes, I have seen the SpaceX launch and land. It's pretty awesome. We're located in Melbourne, Florida, and as part of FIT, well, Florida is not any better than Atlanta for observing, so we don't really get to observe on campus. So we have access to 1 meter class telescope, part of the SARA consortium. One is located in Arizona, one is in Chile at CTIO, and the other one is at the Canary Islands off the coast of Africa. And so with these telescopes, we have primarily photometry capabilities, but we do have some spectroscopy with the Arizona Kitt Peak telescope. Typically, this is how we operate the telescopes. Those are my students on one night of observing. So we actually, they're remotely operated, so we don't actually travel to a telescope. So we get about 30 nights every 6 months, so it's 60 nights a year on the total over the 3 telescopes. This just happened that I left the room and came back and they were doing this. And I'm like, guys, come on. It's I was gone 5 seconds, but yeah. And it's not all about massive stars. Anybody want to take a guess to what this is an image of? Not you. It's a comet, yeah. So if you notice this guy here, it's kind of looping back and forth, but there's this guy here that's moving with respect to all the other stars. That's our interstellar visitor, Borisov, the comet that we got to take with the telescope in the Canary Islands just 2 weeks ago. So that's something that we're also working on for fun. Anyway, so back to massive stars, just a little fun fact. So there are a lot of observational limitations. There are very few O stars. They're about 1% in terms of numbers, but often they're about almost a significant fraction of the light that we see. They're fairly distant. The closest massive star is Saida Ophiuchus, which is about 140 parsecs away. That's the closest one. And, again, looking at the solar neighborhood, how many B stars that you guys have parallaxes for? Is it 1? Yeah. Yeah. And then they also go through their lives very quickly. They just live a few million years, which on our time scales is very long, but in time scales of the universe, it's not that long. So trying to catch them, especially during when they're being in their formation process, is actually quite difficult, because that is also much shorter, and it all happens inside clouds of gas and dust. So we usually don't get to observe their birth, but because they only live for such a short period of time, they're by definition young. So a lot of the properties that we can observe of them during their main sequence lifetime we can use to kind of infer more information about their formation. So where do we go looking for massive stars? So this is an image of Cygnus OB2, which is an OB association. The Orion cluster, which is one of our nearest cluster of massive stars, has quite a few. And this is an image of R136, which is actually in the Large Magellanic Cloud. And so you can see that these kind of environments, while these may look fairly similar, this one kind of looks a little bit different, right? And so where in particular do we go hunting for very massive stars? Remember, those are the guys that are over 100 solar masses. So in the Milky Way, we just from the simulation we saw earlier, it makes sense that we want to go looking for them in clusters. And one of the clusters that is best known try to go after massive stars is the Arches cluster. It's only estimated to be about 3.5 million years old. So if massive stars lived only a few million years, it should still have most of its massive stars. And basically the two brightest guys, the two most massive guys in the cluster, are 185 and 165 solar masses each. So Arches cluster, we have two guys over 100 solar masses. There's also NGC 3603. It's about 1 to 2 mega years, a little younger. And it also has two members. One is a binary system in which one of the two is over 100 solar masses. The other one is close to 100 solar masses. And then it has another member component, B, which is just another star that's also over 130 solar masses. So another cluster, a dense population. We can get in our mass, build up these stars to get to over 100 solar masses. But there's other places that we can look that's not just cluster cores. There's Eta Carina, which is kind of outside of a star formation region. And it's a sort of 120 solar mass star, and it's also a known binary star. Noticing a pattern, many of these are binary stars. And there's this guy in Cygnus OB2 that's also over 100 solar masses. Notice the different environments, not a dense cluster, and it's also 120 solar mass primary, and it's possibly a triple system. So it's known to be a colliding wind binary, but I'll come back to this, but there's a third companion that we found that's further out. And so to scale, this is Cygnus OB2, this is Orion, and this is R136. So they're quite different environments that we're finding these very massive stars, right? So are the properties of these massive stars universal, despite the fact that we're talking about very different scales, the fact that you're still having somehow in this much larger area, volume, to build up your star to masses over 100 solar masses? Can you do that in such an environment compared to Orion and R136? So I'm going to talk about particularly Cygnus OB2 and R136. So this was primarily my work here with Doug. Cygnus OB2 is an OB association. It's about 1.4 kiloparsecs away. It's the closest OB association with a significant number of O stars. So there are about 100 O stars in it. It's relatively young. It's between 2 to 5 million years old. It has quite a bit of mass, 40 to 100 solar mass per, sorry, total mass is 4 times 10 to the 4 solar masses, but it's not very dense, right? Per parsec, there's maybe about like one star, one massive star per cubic parsec. And so this is what the main sequence looks, or sorry, HR diagram looks like for the members of Cygnus OB2. And if you guys remember, one of the very massive guys I mentioned earlier, Cygnus OB2 number 12, is sitting up here. It's that guy up there, right? So most of the stars are following main sequence types, but this guy, which is also the most massive guy, is much brighter and kind of cooler, but probably a little bit more evolved than the other guys. But just remember that even though stars can be giants, they are still on the main sequence because O stars, that supergiant O stars are still main sequence stars, so they're not dead yet. And one of the things that has been established pretty recently, so just looking at what Cygnus OB2 looks like today, you can tell it's a very low density environment. But has it always been a low density environment is the question, because we have these massive stars. Well, at some point, was this a denser environment that kind of spread out? And so work done by Wright et al. Have found that basically Sig OB2 has always been a low density environment. And so there was never a sort of cluster in Cygnus OB2. And there has been spectroscopic work done on the O and B stars of Cygnus OB2 that gives us a fraction of about 30%. So a third of the stars show a spectroscopic binary in this low density environment in Cygnus OB2. So the work I've done was primarily to look for wide binaries, and using two campaigns, mainly using AO with Gemini North and interferometry with Hubble. I'm not going to bore you guys with interferometry because you're all experts, right? But Hubble interferometry is a little different. So this is our sample of stars in SIG-OB2 that we went after with both NIRI on Gemini and Hubble, FGS. And those are basically kind of the colors equivalent to the primary of each of these. So bluer stars are blue, redder stars are red. So guess which one that guy is? That's SIG-OB2 number 12. And so we, with the AO, were able to do multi-band photometry for each of them. And what you can see here is you can see 1, 2, 3, 4 stars, right? And notice the color of that guy, right? So we only have single snapshot of these guys. We don't observe them over time. And so what's the likelihood that these guys are actually gravitationally bound? That's the question we have to answer. And if they are gravitationally bound, why is this guy so red? And then just to give you a view of what the FGS data looks like. So this is a little bit different than fringes on Chara, but similar concept. So they're called S-curves. So each little S-curve is a star, but it gives it to you along one axis. And so I've kind of drawn approximate what each of these axes corresponds to. So it's a scan along this direction for the Y and a scan along this direction for the X. So you can imagine that with the X direction, basically stars 2 and 3 kind of overlap. But then if along the Y direction, you can actually resolve stars 1, 2, and 3 is that little guy right there. And this is the NIRI image for the same object. And so we were able to measure separation and differential magnitude, which corresponds to about several hundreds to thousands of AU in Cygnus OB2. The most massive companion is MT421, which is this guy. We've discovered about, I want to say, 30 or 40 stars in this field around MT421. And you can see that it's in this area here. I'm trying to figure out where it is, actually. It should be, there's a lot of overlaps. But you can see that this is also the most densest region in Cygnus OB2. So it can kind of make sense. Maybe it's possibly a leftover filamentary structure that allowed for the formation of the massive guys. And so just to kind of give you an idea, this is about 10,000 AU from the primary. And so every circle is a star that we detected. And 10,000 AU would allow for a star to orbit at least once in the lifetime of the stars. And so not necessarily every star within a 10,000 AU projected distance is likely to be a companion. So we just did a probability based on the surface density around this field to determine how likely is it that we would find a star of this brightness at this distance from the primary star. And so everything in red is not likely to be a companion. It's just statistically randomly possible that it's just there along line of sight. But these guys are the most likely to be gravitationally bound to that guy, even though there's about 30 or 40 stars in that field. Now, this is SIG-OB2. This is the really massive guy, the very massive guy. And this is the NIRI image, and this is the FGS image of it, S-curves of it. And so what you're seeing here is that if it's inside the shaded region here, if the S-curve is in that, the residuals of the S-curves are within that, then it's not a detection. But you can clearly see that this goes well beyond the residuals of our S-curve. So meaning that this is likely to be a resolved binary somewhere in here. Very close, about on the order of 64 milliarc seconds, sorry. But in the AO image, we also found this third guy, which is about just one over arc second away, which corresponds to about 90 AU for the FGS detection and several thousand AU, almost 1,500 AU for the AO detection. So this is also a known colliding wind, which they estimated to be about 40 AUs away. There's a large error bar here. So it's also possible that this guy that we resolved with FGS could also be this colliding wind binary that they discovered and they observed in 2017. So here is just a distribution by spectral type of the multiplicity of the number of companions. So we only had total 75 targets, so this is by no means something that's statistically meaningful, really, especially on the number of all these bins. But it's just to kind of give you an idea of, basically there's not necessarily an observed drop-off as you go to later type, because this is pretty much random throughout. So it's pretty flat throughout the spectral regime that we looked at. So just from our AO and interferometry, we got about a multiplicity fraction about 42%. If we fold in the spectroscopic binaries from Kobalnicki and Kaminski, this raises it up to 64%, and this is not taking into account any biases, like any observational biases that we may have. This is the lower limit for the multiplicity fraction for Cygnus OB2. And so with that, we have about 27 single, 27 binaries, 12 triples, and 9 systems with more than 3 stars or above. So what you can see is that not only are they binaries, but there are multiple systems, and there's a lot of multiple systems out there. And so going back to the idea that, okay, so Cygnus OB2 is a very low density environment, and we're seeing these wide binaries is, again, I just had one single snapshot, so is it likely that we would see so many wide binaries if Cygnus OB2 had a denser environment at some point, right? And so this was a work done by a grad student at Sheffield, and they basically ran several simulations. And what they found is that of the binaries that we found, if there had ever been another massive star with it that it could have gravitation interacted with, those star systems would have been interrupted. So the fact that we're seeing them and they haven't been destroyed confirms the idea that this had always been a low density environment, and we're able to form these massive binaries in a much lower density environment than most models kind of assume when doing massive star formation. And just kind of like to kind of summarize the mass ratio distribution of massive stars, this is work done by several other people. And the idea is there's no excess of twins. So our observational techniques tend to prefer stars of equal mass typically. Those are the easiest to detect. But if we do take into account our observational limitations, there really isn't more twins than stars with unequal mass ratios. And so basically, we should be able to look for low mass companions, especially low mass companions at wider separations. And so just to kind of, for galactic plus some LMC stuff, the mass fraction for galactic O stars and overall is about 70%, with companion fraction about 1.9, meaning that most stars have more than one companion, right? So if they had one companion, this would be 1, right? So this is close to 2. So triples are actually quite common. And one of the things that came out, because we had multiple photometry for the adaptive optics data set, we were able to do some color magnitude diagrams. And yes, there's a huge scatter, but there's noted very red, bright objects here. And so the question then is, are these actually foreground red objects that we think are associated with the primary star? Or like they're just line of sight, they just happen to be associated along our line of sight? Or are they actually red objects that are associated with the massive O and B size stars, meaning that they will still be pre-main sequence objects, right? Because they're brighter, they're redder. And so I still have a project on this looking at the spectroscopy of these guys to kind of give us a better idea if these are pre-main sequence objects or foreground red objects. So now moving on to the other question of what is the most massive star. And so typically why most stellar population codes and why so evolutionary codes cut off at about 100, 150 solar masses is because people have looked at different clusters and tried to estimate what should be, from the mass of the cluster, from what we have now, what should be the most massive star that cluster produced any time in its history, right? So it could be that that star is gone, but did it ever, what's the most massive star it could have had? And so if you guys remember, we talked about arches earlier. And that's the main cluster that people have looked at and have come up with basically the most massive star that arches could form was 150 solar masses. And so because arches is a typical cluster, we can then apply that to pretty much most clusters that no stars can really be over 150 solar masses. The other idea is basically the Eddington limit, right? So if your star is of a certain brightness, it's going to for it to be in hydrostatic equilibrium, it has to be underneath its Eddington limit, meaning it's not going to be so bright it's blowing itself apart. And so if you follow the traditional mass-luminosity relationship of L is proportional to mass to the third, then you reach a point where that you get a mass where you would exceed your Eddington limit, right? And that's, again, around that 100 and 150 solar masses. But to be honest, from empirical data, we see that this is not the case. As you go to higher and higher masses, the mass luminosity relationship goes to 1. And so you can get to higher and higher masses without actually exceeding your Eddington limit. You can get close to it, and stars there are variable, but you can get to very, very massive stars without it actually having to exceed the Eddington limit. So that brings us to Large Magellanic Cloud. So this is one of our neighbors, and in particular, this guy here is a Tarantula Nebula. It's a very large star-forming region, so it's 200 parsecs across. And it's interesting because one of the theories for why this this small galaxy, right, that has very little gas to it, has this huge star-forming complex, and it's thought to be kind of triggered because the Large Magellanic Cloud is has some friction as it's passing by the Milky Way, and that is where that friction is kind of triggering star formation in the LMC. So this is a close-up of the Tarantula Nebula. And in the Tarantula Nebula, there's several very massive stars. So I don't know if you guys remember how many I counted that we know of in the Milky Way, but you can count them in your hands, right? This is just a 200 parsec region of the Large Magellanic Cloud, and there's already 1, 2, 3, 4, 5, 6, right? And if you look there, there's actually even more just in that space as well. So that's R136. It was discovered in the late 1800s as part of the Radcliffe Observatory catalog. So that's what R stands for. So it's the 136th entry in the Radcliffe catalog. And in the 1960s, they did some photometry of R136. And from the photometry, they estimated that this should be a 2,500 solar mass star, right? And yeah, that's ridiculous. So this star is really interesting because it went back and forth. It's like, we have stars of 2,000 solar masses. No, they can't exceed 100 solar masses. And so with better and better technology, they were able to find that, hey, that's one thing that was R136. There's 4 bright things in there, with A being the brightest of the 4. And even A is still thought to be really, really bright, really, really massive. And this is 1980s. And it wasn't until interferometry that we were able to resolve A into 8 different components. So that 2,500 solar mass star is actually this 8-component cluster, with A1 and A2 being the more massive members. And so we went from 2,000 solar masses. Now we have it broken up into 8 stars. Yeah, it still agrees with our 100 solar mass limit. And we were finally actually able to image it, even though this is not a great image. This is a Hubble image from the 90s of A1 and A2. So up to this point, the only reason we know A1 and A2 were separate stars was through interferometry, a full decade before we could actually image it with Hubble. And so A1 and A2 are the most massive members of R136. So this is another beautiful Hubble image of it, much better image. And A1 and A2 are in there. It's a much higher density environment. It's a lower metallicity environment, but it's also a much younger environment than Cygnus OB2. The work that I've done focuses on the very central parsec core of R136, looking at A1, A2, and many of those stars that are in there. So what we did was we had a STIS spectroscopic survey where we lined the slit up along this direction and basically offset a total of 17 slits so that we could cover the central region of R136. And we did it in 5 different wavelength bands, 6 different wavelength bands, UV, 4 blue, optical, and H alpha. So yeah, and so we were looking for basically binary stars, spectroscopic binary stars in this central parsec region of R136. And so if we look at this region, remember there were 6 outside of R136? Well, there's several more in this, just around R136, of very massive stars. So this by far blows away the Milky Way. And just, this is not even in 200 parsecs. This is in just a few parsecs. And in the core of R136, we have, these are the stars resolved with interferometry. We have B and we have C. And from our UV data, we estimated that R136A1 is on the order of 300 solar masses. Plus or minus quite a bit, but on the order of 300 solar masses. Basically, we know R136 definitely exceeds by far the 150 solar mass upper limit. So we have to take into account these more massive stars when doing our solar evolutionary codes and our solar population codes. This is a preliminary IMF for our R136. Apologies, I have a more updated one that actually shows a clear kind of double bump here, implying that there might have been two star formation processes in R136, a very young one down here and a slightly older one over here. Yeah. So in it, so far, we've found spectroscopically about a third of them are in a binary. This is similar to the work in SIGWI 2, if you guys remember, with the spectroscopic campaign. About a third of them were also found to be binaries. And so we haven't finished the analysis yet, but this is consistent with the 70% to 100% binarity from Milky Way binary work that I just mentioned. So this is, I just highlighted here the guys that we've found to be binaries. Okay, so we have this 300 solar mass star in the center of R136. Are we sure it's a single star? What are the things that can affect its mass, right? It's the first one would be that it's a binary, right? So if it's actually two stars that we haven't found spectroscopically because the period is too long, or we haven't found spatially because you guys saw those, this is a very dense field, and even with Hubble imaging, we can't resolve the center of the course. So, but for us to still maintain within that 150 solar limit, both stars in our binary would have to be around 150 solar masses. So one possibility is that it was a merger at some point. That's something that's hard to exclude from this. There's no current evidence that this was a merger of any sort, but we can't actually exclude that at this time. We can look at it spectroscopically, and that probes about 90 AU region, and that was looked at by Schnurr et al. They didn't find any evidence for this to be a spectroscopic binary. They looked at it to see if there was any evidence for colliding winds, and that probes in the 3 to 300 AU range, much further out. They did not find that there was any evidence for this to be a colliding wind binary. And then the question is, can we resolve it, right? And so we have a data set that we're still working on of looking at the core of R136 with FGS, with Hubble FGS. And you can tell, so this is our cluster. I was going to show you, it's supposed to show you the FGS scans for both of these regions, but you can tell this is just so dense that it's really hard to disentangle each member in the S-curve. So that's works right now is still ongoing. So to kind of give you an idea of the sensitivity of the Hubble fine guidance sensors, this is comparison with other high spatial imaging methods, so interferometry, adaptive optics, Lucky, speckle, seeing limited photometry, and spectroscopy. Delve kind of very close in. These guys delve a bit further out. And FGS is really good at finding wide, long period systems that are near equal mass, right? So this is ideal for looking at R136. But the problem is that there's a lot of background and field stars with interferometry. The way that Hubble FGS are different than, say, Chara is that instead of having two telescopes, you actually have you split the beam up of your incoming light, and then re-add it together to get your interference pattern. Here we go. Sorry. So these are the S curves, and so this is where A1 is, this is where A2 is, A2, A1, and you can see there's still like a lot of signal from pretty much all the other guys behind it. So we're still trying to disentangle that and model what the cluster around it is doing and what we're picking up with the FGS S curves. So what I'm showing you here is the integrated spectra of the UV spectra of the massive stars that we observe with our STIS campaign. And so what you're seeing here are the very massive stars, right? The stars that are over 100 solar masses in red, the stars that are not, that are under 100 solar masses that we were able to separate out. And this is the total integrated spectrum of R136 just from the stars that we observe. And so there's about 30 very massive stars just in the core, in the Tarantula Nebula. And they've studied by Doran et al. Found that about 50% of the ionizing output, so the UV, is coming from just 30 stars in that whole 200 parsec region, right? But here, we're just looking at the central parsec. And what you'll notice is that certain features, like this one here and this one here, are completely just coming from the very massive stars. And these stars there were only 8 stars that contributed to this. So these 8 stars dominate these features in the integrated spectrum of this cluster. And so if you look at another cluster, that similar cluster, or cluster in a nearby-ish galaxy, NGC 3125, you see this helium-2 emission line. You see this little bump here. And so basically, these features are made from basically a handful of stars. And so for our ability to understand, hey, we have very massive stars in our cluster, so we need to be able to integrate and include their light, especially when we're doing stellar population synthesis models, when we're looking at the, sorry, wrong one. Yeah, when we're looking at the integrated light from something we cannot resolve, then we really need to include, we need to know how many very massive stars are in our cluster to give us this feature, right? So where do we go from here? Is basically doing a study of nearby resolvable counterparts to clusters or galaxy features that James Webb will be observing. So James Webb will be looking in the infrared, but for a high redshift, that infrared light is actually UV light that's been redshifted. So we need to be able to know the contribution for massive stars to that, what we're going to be seeing with James Webb, and to do high spatial observation campaigns with the next generation instruments such as ELT and current instruments that we have, SPEAR and GPI, to look at what is the actual multiplicity fraction and companion fraction for massive stars. So we want to look at this in a variety of environments. I showed you some, but in a variety of different metallicities and a variety of different cluster ranges, and double check that what we're seeing is universal. So this is a AO observations that we have of M17 with VLT, where we see the most massive guy. We resolved it into binary. Extended to lower mass stars like B stars, especially BE stars, Doug's favorite for those of you who are working with Doug. And kind of these guys are the ones that are most likely to be the progenitors for supernovae, like core collapse supernovae and things like that. So understanding the role that, getting a complete multiplicity fraction will help us predict how many we should expect to see. Does that match our observations? Does that match our observations for the number of gravitational waves we're observing? And basically using high spatial, high contrast techniques to study these environments of massive stars. So going back to my motivation questions, are binary properties universal? Yes, but triples may play a larger role than we thought. What does this tell us about star formation and stellar evolution? Basically, you don't need high density environments to form massive stars. And we need to include binary stars in our stellar evolution and stellar population codes. And what is the most massive star? R136 is the one we know, but there could be more massive stars out there still. All right, thank you very much. Gonna have to speak a little louder. It depends, because LMC, that's like 20 something. Like they're really faint, but the ones that were in SIGOB 2, I'm trying to remember. So we looked at them in the infrared because there's a lot of reddening. So in the visual, they're actually not quite that bright, but they had to be brighter than 15th magnitude for us to be able to do FGS survey. They're probably on the order of like 10 to 15 in there. That's just SIGOB 2. We tried SIGOB 2 number 12 with Chara, and we weren't able to get anything conclusive with that. So, not yet. Yeah, but we're actually, that's one of the ones I'm trying to get time to do for the B-star multiplicity fraction. So, yeah.
I was wondering how the mass loss of these stars will play a role in mass determination.
Mm-hmm.